What happens when things burn? This cylinder is filled with oxygen. In oxygen, the candle burns brilliantly and is consumed very quickly. Let's try some other substances. This is red phosphorus. This is sulfur. And this is sodium. Like the other substances, it too burns more brilliantly in pure oxygen. Even steel burns quite quickly in oxygen. This crumpled copper foil also burns quickly in pure oxygen. There must be a relationship between burning, which scientists call combustion, and oxygen. Here is another sheet of copper foil. Let's burn it in a flask containing only oxygen. In order to fill the flask with pure oxygen, we must first use a vacuum pump to take out the air already in it. Oxygen is let into the flask. Now the flask contains only copper and oxygen. The copper is gradually heated from outside. Suddenly, it burns. A black ash is produced. The black ash is not the same substance as the copper. To demonstrate this, copper and the black ash are put in separate test tubes, and some hydrochloric acid is added. If the substances are the same thing will happen in both tubes. The copper is not changed by the hydrochloric acid, but the black ash is. After a few minutes, the copper is still the same, but the solution in the other tube has turned green. So the black ash does not have the same properties as copper. What is it? Scientists use the idea of atoms to explain what happened in the flask. Because atoms are too small to see, we will use models to represent them. Here, red balls represent the oxygen molecules. As they are heated, they move more quickly, often striking the copper atoms represented by the yellow balls. When an oxygen molecule hits a copper atom, it breaks into two oxygen atoms. And each of these combines with a copper atom to make a new molecule made of one copper atom and one oxygen atom. These new molecules are the black ash. Copper and oxygen combine to form a new substance, copper oxide. The burning of copper is a chemical change. So when copper burns, the black ash that results contains both copper atoms and oxygen atoms. But if some of the oxygen atoms are now contained in the ash, there ought to be fewer free oxygen molecules in the flask after burning has taken place. Is this so? To find out, let's do another experiment. Some copper is put in a tube. Oxygen is let into the tube, which is also connected to another tube containing a water jet. Both tubes are sealed except that the water jet is connected through a valve to a pan of water. When the valve is opened, the water does not enter the tube because the pressure of the oxygen inside keeps it out. The copper has burned. Are there now fewer free molecules of oxygen in the tube? Let's turn on the water again. It does enter the tube, taking the place of the oxygen atoms that have combined with copper atoms. Let's compare the weight of the copper and that of its ash. First, 2 pieces of copper foil are placed on the pans of a balance. They weigh the same. Now, one is burned. The burning copper is gaining weight. Where does the extra weight come from? All atoms have weight. The burned copper has gained the weight of the oxygen atoms which combined with it. Do all things gain weight by burning? The candle becomes lighter as it burns. Why doesn't it become heavier, gaining the weight of the oxygen atoms that combine with it? Through special photography, we can see gases coming out of the flame. These gases produced by the burning candle are carbon dioxide and water vapor. The gases contain many atoms from the candle. When they escape, the candle naturally loses weight. This is sodium hydroxide, a chemical that absorbs both carbon dioxide and water vapor. A container filled with sodium hydroxide is put above the candle so that the gases coming from the burning candle will be absorbed. Now, let's do the experiment again. The sodium hydroxide is changing as it absorbs the carbon dioxide and water vapor produced by the burning candle. Special photography is used to speed up the action. 10 minutes burning is shown in 10 seconds, so that we can see the movement of the needle on the scale. The side with the burning candle is becoming heavier. Things which produce gases when they burn seem to lose weight. But if we trap these gases, we will always find that the burning substance will gain the weight of the oxygen that combines with it. This screening is made of copper. When the copper is heated, it combines with the oxygen of the air, forming black copper oxide. What would we have if we remove the oxygen atoms from the copper oxide? In this experiment, we'll use hydrogen gas to remove the oxygen atoms. Hydrogen combines very readily with oxygen. Hydrogen coming from a gas tank is purified and dried before entering a tube containing the copper screening. The waste hydrogen escaping from the other end of the tube burns, combining with oxygen atoms in the air. Now the copper is heated. Gradually, the screening changes color. The black copper oxide has become pure copper again. What happened to the oxygen? Water drops are forming at the end of the tube, though the hydrogen was dry. Hydrogen, represented here by white balls, combines with oxygen, the red balls, more readily than copper does. So the hydrogen atoms take oxygen atoms away from the copper oxide to make water molecules. The pure copper is left behind. Copper oxide and hydrogen have formed copper and water. Water and copper. The copper burned, producing copper oxide. But the atoms of copper remained unchanged. No atoms are destroyed in a chemical change. In this flask, another chemical change is producing a gas called carbon dioxide. A molecule of carbon dioxide has both carbon and oxygen atoms. The cylinder is now full of carbon dioxide. Carbon dioxide is often used in fire extinguishers. But some substances burn very well in carbon dioxide. Magnesium, for example. And sodium. These substances combine with oxygen more readily than carbon does. They can therefore burn by taking oxygen atoms away from the carbon dioxide molecule, just as hydrogen took oxygen atoms from the copper oxide. This is liquid oxygen. Its temperature is more than 300 degrees Fahrenheit below zero. Even at this low temperature, substances burn furiously because of the plentiful supply of oxygen atoms. So not all combustion takes place at high temperatures or even in the presence of free oxygen molecules. But whenever things burn, atoms of oxygen are uniting with atoms of the burning substance to produce new molecules.